Sections 10.2 and 10.3 deal with arcs and chords in circles. So open up your notebooks, get this into your table of contents, and we'll begin with some vocabulary. So, some basic circle vocabulary. Take a minute and sketch that circle with the various segments drawn in. If we wanted to give the circle a name, we name circles based on their center points. So I would call this circle E. Alternatively, you can use this symbol, kind of a O with a dot in it, that represents circle E as well. Next, if I asked you to name a radius of the circle, you have a bunch of different choices. You could say segment AE, segment BE, CE, or DE. They are all radii of the circle. Next, name a chord of the circle. Now, a chord is a segment with both endpoints on the circle. So we could say, for example, AB is a chord. AD is a chord. If I ask you to name a diameter, of course a diameter is essentially the length across the circle, so we could say AC or BD. Now note the definition of a chord matches the definition of a diameter, right? A diameter is a special type of chord. A diameter is a chord that goes through the center of the circle. And so therefore AC, even though it's a diameter, it's also a chord. Likewise BD is also a chord. So some more vocabulary. Central angles. Here we have a different sketch. Central angles, it's just an angle in the center. So for example, angle ABD, DBC, these are both central angles. An arc is a piece of a circle. So for example, that little chunk between A and D would be considered an arc. Or the length from D over to C would be considered an arc. A minor arc is an arc that measures between 0 and 180 degrees. So for example, arc AC would be considered a minor arc. You'll notice we put kind of a little curvy arc over top of the letters to indicate which arc we're talking about. So minor arc measures between 0 and 180 degrees. A major arc measures between 180 and 360. And so we would say, for example, arc DFE is a major arc. We always measure major arcs, we always name major arcs using 3 letters. So D, go in the direction of F, end up at E. That would be your major arc. And then lastly, a semicircle, of course, is just half of the circle. We can either refer to the top part, that red arc JKL, or JML would be the bottom arc. So let's work with a few examples here. Take a minute and sketch yourself circle E, and we have a bunch of radii drawn in. We've got a right angle, we have a 150 degree angle, and we're going to start by discussing arc measure. Now, arc measure is essentially how big is the central angle that is cut off by that arc. So for example, if I asked you for the measure of arc AB, I see the angle that cuts that off is 90 degree angles. And so that arc, its measure is equal to 90 degrees as well. If I ask you for the measure of CD, well, that's just equal to its central angle. And its central angle, we see we have a semicircle, which is 180 degrees. Subtract 150, we have a central angle of 30 degrees, and so the measure of the arc is equal to 30. If I ask you for a measure of arc CDA, so that's a semicircle, so that's just equal to 180. If I ask you for CAD, that's different. Now I'm going to start at C, and then follow the order of the letters. C, go in the direction of A, end up at D. And so we're going the long way around the circle. So instead of 30 degrees, we actually have the remainder of the circle, so 330 degrees. So that's arc measure. We also have arc length. Now arc length, it takes the central angle divided by 360, multiplies that fraction by the circumference of the circle. Now, in order to get circumference, we of course need a radius. So let's pretend like this circle has a radius of 6. And now I'm going to ask you for the arc length of AB. You'll notice on the right side we've got a little m out front. That stands for measure of the arc. On the left side we don't have that m. That indicates that we're measuring arc length. So arc length of AB is central angle over 360 times the circumference. So we would have an arc length of 3 pi units. Likewise, if I ask for the arc length of CD, I'll take its central angle divided by 360 times 12 pi, and that simplifies just down to pi units. Likewise, arc length CDA is 6 pi units, and arc length CAD is central angle over 360 times circumference, so we have 11 pi. Next, I've got a theorem for you. So this theorem states, in one circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So in other words, we've got a circle, and we have these two minor arcs. Let's say arc AB and arc CD. I know that those two arcs are congruent if and only if the chords that correspond with them are congruent. So kind of like contact lens-like shapes. Here's another theorem. In a circle, if a diameter or a radius is perpendicular to the chord, then it bisects the chord and bisects the arc. So let's draw ourselves a circle with a diameter and a chord that runs perpendicular to that diameter. This theorem states, if they are indeed perpendicular, then the chord is bisected, and also the arc that is sort of made by that chord, that arc is bisected as well. We have one last theorem. Last theorem states, in a circle or in congruent circles, two chords are congruent if and only if they're equidistant from the circle's center. Oh my. So, we know we have a circle, or maybe congruent circles, and it says two chords are congruent, so I'll draw two chords. Those chords are congruent in length if and only if they're the same distance from the circle's center. So that distance and that distance must be equal. So we have those three theorems, and we're going to apply those three theorems to a couple of sample problems coming up next. First example, take a look. We've got this circle W. We have a diameter drawn in, and we have a chord. And we say, let's say circle W has a radius of 10. WL is perpendicular to HK, and HK is equal to 16. And we want to find the length of JL. So we know the radius, that's 10. We know we have perpendicular segments, and we know HK is 16. Now remember from that previous theorem, if a chord is perpendicular to a radius or diameter, then that chord is bisected. And so that means HJ and KJ are both 8, right? They're half of 16. Now, we want to find JL. The trick with this is, remember, all radii in a circle are congruent. And so if you draw in, let's say, radius WK, then we have a triangle, JKW. And we can find the missing leg using the Pythagorean theorem. So x squared plus 8 squared is 10 squared. That gives us that the length JW is 6. Since the entire length is a radius, if the part above is 6, the part down below has to be 4. Sort of a second problem on this one. Let's say we want to find the measure of arc HK. Remember, the measure of the arc is equal to the central angle. And so we need to find that central angle. Well, we know that arc HK is bisected. And so if I just found that one angle, I could double it. Well, again, take a look at that triangle, JKW. We want to find the measure of angle W, and we know we have a right triangle, so we can just use inverse, sine, cosine, or tangent. I happen to use tangent for this case, so that gives me an angle of about 53.1 degrees. And so if you double that, you'll get the measure of angle HWK. And remember, the measure of the central angle is congruent, is equal to the measure of that arc. Let's take a look at another example. Sorry for the sloppy circle. Take a look, we've got two chords and a circle P. So take a minute and sketch that out. And let's say we're given that chords EF and GH are equidistant from the center of circle P. And so that tells me that not only are those two right angles, but those distances are the same. Likewise, we know that those separate distances are broken up. Since EF is equal to 24, I know that half of 24 is 12, so all those little segment lengths are 12. And we want to find length PR. Well, just like in the previous example, you're going to use radii. And so if you look at triangle PRH, I know x squared plus 12 squared is 15 squared, and so therefore PR is equal to 9 units.